Good afternoon, everyone. Thanks for coming to the Extreme Performance Series talk. And this talk will focus on vSphere CPU scheduling and memory management related issues. First, I have to admit that these slides are not created by me. The engineer created the slides cannot come because of visa issues. And I also just noticed that some of the slides are not in the same order as I prepared. But don't worry, I'm a principal engineer at VMware, and I spent more than 10 years developing and tuning CPU scheduler. And actually, most of the year's CPU scheduler is written by me. So in some sense, I own the CPU scheduler, and I'm one of the best engineers at VMware for your CPU scheduler related problems. So let's get started. So normal disclaimer. And let's start with I will skip a few slides that I didn't prepare for. Let's start with my favorite topic, CPU scheduler. So I suppose everybody here just had lunch. And at lunch, we have multiple tables. Each table you have a queue, right? So that's a basic kind of scheduling problem here. We have two problems. First, for each queue, who gets service first? And the second problem is you have multiple queues and they move at different pace. Sometimes you move to another queue that is shorter. Right? That's a load balancing questions. So CPU scheduler is exactly the same kind of setup. It's a distributed scheduler, meaning when a system most systems have many cores, like for example, a system can have 32 cores. And with hyper-threading enabled, you have like two hardware threads for each core. So you have 64 PCPUs or hardware threads. And the CPU scheduler have one queue for each hardware thread, just like one queue for each table at lunch, right? And it makes local decision, which means for all the threads queued for a certain queue, which one should get service first. And let's talk about this first. For lunch, the people enter the queue first, get service first. So it's just like a classical FIFO scheduler. That's very, very simple. The ES scheduler is more complicated. So it mainly considers two numbers. One is the usage, how much CPU time a thread has used, and its allocation. Let me do a quick survey. How many people here have played with resource pool and like IL's limit reservation shares? How many people have played with that? Okay, like kind of half and half. So it's kind of good and bad. So for positive side, it means I saw some people have never played with that. It's on the positive side, it means our CPU scheduler kind of work out of the box. It's the kind of ultimate goal for any resource management algorithm. Basically, it works out of the box. You don't need to tune anything. On the other side, I would recommend you to read more about this, like resource pool, reservation max limit, because it's a very useful tools, especially when you want to do some differentiated service within a host. Like you are running virtual machines, and some virtual machines are more important than others. Then resource pool is a very useful tool to achieve that. And we have a detailed like resource management guide for this topic. I will recommend to read up that. So going back to the talk, with resource pool setting, when you set all the reservation limit shares, it translates to your allocation for each VM. So each VM has certain entitlement. And ES also dynamically monitor the usage and compare it with your entitlement, and it will always give you a high priority if you use less than your entitlement. So if you wonder if you set all the resource settings, how it maps to local scheduler, this is why it matters. We consider for a local scheduler, for a certain queue, we give the one that uses less than its allocation a high priority. That's local scheduler. The next topic is the load balancing. Load balancing is a very complicated, like sophisticated algorithm. I spent years just tuning that. It mainly tries to meet two requirements. First requirement, we want to avoid the situations that one CPU has multiple threads waiting queued there, another thread is totally idle. And for typical modern systems, it actually happens very frequently. If you have an IO thread that has 10,000 or even 1 million IOPS, it basically means the thread comes and goes at multiple microseconds level. Transition to scheduler, it means a queue, a certain PCPU can switch between basic and idle states very, very frequently. And so ES scheduler need to decide when to move something in or when to let it stay idle, for example. And if you want to achieve, that's the one requirement, basically try to maximize the utilization on a very dynamic environment. Another requirement is overhead or scalability. Looking if you for launch, if you just scan the one queue and go to the other one, it's very cheap, right? But in a computer system, it's a very expensive operation. A big system can have hundreds of cores, and if you scan all the queues, it's very, very expensive, not just because of the CPU time needed to make the decisions, but also while you are scanning, you are polluting out of the cache. That's very, very expensive when you are running at a very high frequency. So yes, CPU scheduler did a lot of tuning to strike the balance between high CPU utilization and scalability, low overhead. At a high level, we consider many things. We consider cache state. We consider migration cost. We consider hyper-threading, cache contention. For big VM, we consider where the sibling CPU runs. And we also consider VM to VM communication, consider many things. But overall, I think we did very well in this area. And we have, in most cases, you do not need to worry about this because we already have achieved a good balance between overhead and utilization. But if you see any problem, let me know. Okay. So I suppose most people here want to dynamically monitor the system performance or virtual machine performance, right? And ES top is a kind of Swiss knife for system performance monitoring. And it's named after top. It works similar to top. It's basically a command line tools, and you can use to monitor CPU, memory, networking, disk performance related to all these areas. And it can also run in batch mode, and basically you can export it to CSV. You can generate a CSV file, and you can load it into your favorite performance monitoring tools to do further study. And in ES65, we made a few changes, but more or less, it's a very stable tool. It has been there for a long time. ES65, we make a few changes, and we will talk more about that in the later part of this talk. So ESTop has, as I said, ESTop has many pages. Here, I just want to highlight one. If you specify the group ID of a specific virtual machine, you can explain it to a view that reports the stats at a per thread level. So what I want to highlight here is for two virtual CPU machine, you might expect it has 2 threads, but actually it has many more than 2 threads. For example, what I show here, you have MKS threads that emulate mouse, keyboard, screen devices. And you have SVGA thread, which try to emulate the basic display, SVGA display. You might also see some networking I/O, storage I/O related states. The key message here is mostly because of device emulation, we have a lot of more threads than configured 2 vCPU or whatever vCPU number you configured here. So you need to keep in mind when you do capacity planning or do some performance troubleshooting. But in most cases, these threads doesn't consume that much resource, so that's fine. But for example, if you have graphic emulation, or you have networking intensive threads, it can consume quite some resources if you have some basically heavy I/O threads. Let's see. Okay, so let's now talk about a few counters that we often you need to use when you do performance study. And I heard people are often confused by these 2 numbers, used and run. It's actually not that complicated. Let me just make this analogy. Like, for example, let me say just this morning I run for 1 hour, I run like 2 miles. I just made it up. So I run 1 hour, that's a run time. Basically, it's measured in workout time. I run 2 miles, that's another number. It's basically the actual mileage. So used versus run is just basically actual mileage and then the workout time. Run is the actual time is spent on running. The used is actual yield, actual application throughput. So why used and run can be different, right? It can be different for multiple reasons. The most obvious one is frequency scaling. If the CPU runs at 2 gigahertz versus 1 gigahertz, obviously the first one runs twice as fast as the second one, right? Another important reason is hyper-threading. I will talk more about hyper-threading very shortly. Okay, so now slides for hyper-threading. The key message here is hyper-threading for overall, if you use hyper-threading, the overall aggregate performance of the both hardware threads is more than single core performance. For example, we measured the performance based on spec CPU, and overall the performance is the aggregated performance is like a few percent to like 40% higher. So in most cases, we encourage customers to have hyper-threading enabled. But on the other hand, single-threaded performance is worse because it's not really single core. It's like both hardware threads share a lot of resources. So in this case, this figure shows how much slowdown for each hardware thread. So it's in the worst case, we show like 1.9 slowdown, but in some cases it's much better than that. But overall message is the aggregate performance for both hardware threads is higher, but a single thread performance is worse. VMware's ES CPU scheduler basically had a lot of tunings related to hyper-threading. At high level, there's 2 things we did, pretty obvious things. First, if there's a totally idle core versus a core that is partially occupied, we'll certainly go to the totally idle core, right? For the obvious reason. The second is we charge the thread less if a thread is sharing the core with others for all the performance things reasons. And we also have a number of tunings related to like how aggressive we do load balancing based on like hyper-threading, based on hyper-threading. Next one. Okay, here's a more detailed breakdown that shows how how all these numbers come from. Let's suppose a thread. First, just based on the life cycle of the thread, a certain thread. Originally, the thread is at T0 is waiting, and at T1 it wakes up. It wakes up. Once it wakes up, CPU scheduler will be kicked in to make a decision to decide where it should go, right? So it will spend a little bit of time spending on the CPU scheduler. That's basically CPU scheduling overhead. At T2, so there's 2 situations. One situation is we find an idle core or idle hard threads, then it's just directly go to that thread, that hardware thread, that CPU, and start running. But often the case. And the thread can also be slowed down for the few reasons we mentioned before, because of frequency scaling, because of hyper-threading, etc. It can be slowed down. So overall, here are the numbers that you can see from ES top. The wait time, the time you spend waiting. Read time, we actually include both the CPU scheduling overhead and the actual queue time as ready time. And from T3 to T8, we consider as runtime. But the part in the middle is basically it's considered to be running, but it's interrupted by other things. It's called the overlap time. And so overall, I mentioned the difference between used and run, and this is the actual formula. Basically, used is run plus system service time. It doesn't show system service. System service time is basically the part of the time that the system doing service for this particular VM. For example, if a networking package coming, the networking package is the system spends some time on processing the networking packet, and this time it will be charged to one of the VMs, destination VMs. So that's called a system service time. So the user time is runtime plus system service time minus overlap time and minus also slowdown time because of frequency scaling and other things. Okay, so in ES, if you pay attention to ES top, you might notice one difference between ES 6.0 and ES 6.5. For example, in this graph, you see for the similar workload, you see in 6.0 you have a lot of system time, and in 6.5 it has almost no system time. This is actually just some accounting issue. It's fundamentally in the back end, the system works about the same. The only the change we made is originally some system threads, for example, networking processing thread is like out of the, it's not belonging to any virtual machines. But now in 6.5 we moved some of the system thread to the virtual machine, as a part of the virtual machine group. So you see it will be no see so in like so that you no longer see a system time, but instead you see user time of the use time of the virtual machines is all pretty much the same. So overall, it's just some accounting difference. So what happens underlying is about the same. Okay, so next topic is ready time. I think we got a lot of questions about ready time, and people often complain, okay, I have a virtual machine and its ready time is high, what happens, right? So the first key message is, when you read the ready time, make sure you normalize it by the number of vCPUs in the VM, basically the VM size. We often heard complaints that it has, like, for example, in this case, almost 24% of the ready time. Seems a little bit high, but this virtual machine has 128 vCPUs. If you look at the ready time for each vCPU is small, it's less than 1%, so it's not a worry. So whenever you check the ready time, make sure you normalize it by number of vCPUs in the VM. But with that, still, ready time is an important issue because it directly affects the application performance, including both throughput and the latency. In this graph, it basically shows the ready time and the throughput has almost like a linear translation, because ready time is the amount of time you can run while you are runnable. And for latency, it's a little bit more complicated because the ready time is impact on the VM depends on workload. For workloads that are bursty, it can be impacted by ready time more. But overall, the more ready time you have, the worse the latency. So this ready time is something you need to pay close attention to when you monitor the virtual machine performance. Okay, code scheduling. I'm not sure if people heard about this, but the first thing I want to shout out is first, why we do code scheduling. So a system, when it has many virtual CPUs, who's a guest, it assumes all virtual CPUs are running online at the same time. So people will assume all virtual CPUs in ESX will run in parallel, but it's wrong. It's a wrong concept, and actually I have seen many other external websites say, yes, that's GAN scheduling, which kind of assume all the vCPUs need to run in parallel. And I took all the chances to shout out a little ago. We never done GAN scheduling. And why? Because GAN scheduling is very, very expensive. Think about it. If you have a big virtual machine with 128 vCPUs, how can we afford to run 128 virtual CPUs in parallel? Like, if you have to run all 128 virtual CPUs in parallel, that means even if I have 100 CPUs idle, I cannot run this because it cannot support 128 virtual CPUs, right? So we never done that. Another thing is, to coordinate all the scheduling of all the virtual CPUs, you need to do a lot of inter-vCPUs synchronization. That's very expensive. So we never try to do GAN scheduling. Instead, we have a very flexible we relax this policy to achieve both goals. First, we want to make sure in most cases, all vCPUs are running in parallel. We also want to make sure the skew means the progress of the two virtual machines are not that controlled within the same bound. So what we do is we monitor the progress of all the virtual CPUs, and if one virtual CPU runs much faster than the other, we just pause the virtual CPU. So we only need to worry about the faster ones instead of always monitor all the virtual CPUs and make sure they run in parallel. Another key high-level thing I want to mention is if a virtual CPU is idle, it's not running, then we do not need to worry about that because we do not consider that for code scheduling. That's a high-level message you need to know about code scheduling. And if you see high code stop, please basically pay attention to the VM wait counter in ES stop. And in a lot of cases, it can be due to a lot of I/O, for example, swapping or snapshot, and that can cause performance problems if you see VM wait. So you need to pay attention to that. Okay, so much for the CPU scheduler, and the next topic is memory management. So I will skip this one because I didn't prepare for this one. So memory management, at a high level, any resource management algorithm only matters when you have contention, right? If your memory is not overcommitted, then you do not need to worry about memory management. Memory management will kick in once you have memory overcommitment. And let me first talk about a few techniques we use to deal with memory overcommit, and then I will talk about how can we avoid memory overcommit at all. So we have multiple techniques we use to reclaim memory pages when memory overcommit happens. So including page sharing, ballooning, compression, and swapping. And the left ones, the page sharing, the cost goes from higher from left to right, from this way. Page sharing is the most cheap, and swapping is very, very expensive. We'll try to avoid swapping. And if you want to know more details about all these different techniques, I will just search for ES memory management. There's a classical paper, OSDI, I think 04 paper written by Carl Warsberg about this topic. It provides very details about what these techniques means. And so besides the time spent on all the memory reclaim techniques, it itself is expensive. There's another part that can make memory overcommit expensive. That's basically all the page reclaiming technique requires smaller pages. So if we almost enter memory overcommit mode, we'll start to break large pages to smaller pages. And as you may know, most applications works much better when using large pages because you spend a lot of less time on TLB access. So that's why we should try, if your application is performance sensitive, you should try to avoid overcommitting the memory. So how do we do that? Okay. So I think this basically, I will skip this slide. Basically, at a high level, it basically tells if the memory is not, okay, at least I think this page basically says if memory pressure is transient, then we do not do swapping, and instead we're using ballooning and page sharing to hide all the memory pressure, and in the end, the performance loss of virtual machine is minimal. But if the memory pressure is persistent, if you really have memory pressure, memory really overcommitted, then we start to do swapping. And swapping is very, very bad, and you will see real performance degradation. So how do we avoid memory commit? So that's two numbers you need to pay attention to. One is overcommit in active memory and overcommit in configured memory. Configured memory is just straightforward, right? If a virtual machine configured to have 4 gig, it has 4 gig. It's configured memory. Basically, configured memory over committee is basically you aggregate all the configured memory of virtual machines in system and make sure it's less than the host capacity. If it's active memory is different. Even if a virtual machine has 4 gig of memory configured, if it doesn't touch, if it's idle, if it doesn't touch that much memory, then active memory may be small. So overcommitting configured memory is kind of common practice, especially for like VDI style workloads. And in a lot of cases, it has very small, negligible impact on the actual virtual machine performance. But overcommitting active memory is expensive, and you will see significant performance degradation. So in most cases, you should avoid overcommitting the active memory. Okay, so next topic is NUMA scheduler. With the introduction of on-chip memory controller, typically all the modern computer systems are NUMA systems. A NUMA system basically, for a given system with multiple sockets, in most cases, each socket is mapped to one NUMA node, but in some cases, because of cluster on die, even a socket can be split to multiple NUMA nodes. And for less common case, you can have multiple sockets belonging to the same NUMA node. But overall, a NUMA node consists of a number of cores, and it has its local memory. The memory access latency from a core to its own local memory is much faster than remote memory. The memory on a remote NUMA node. That's where the name NUMA come from. And because of this kind of asymmetric behavior, it's at a new challenge to the resource management algorithm, so that the NUMA scheduler need to understand this kind of asymmetric behavior. And we should consider 2 different cases. Let me start with a simple case when the virtual machine is small. When the virtual machine is small, the virtual machine will be placed on a certain specific NUMA node, which we call a home node. I mean, we heard about that. So each virtual machine will have a home node, and all the virtual CPUs of this virtual machine will stay on its home node, and in most of the cases, the memory allocation is also local. So we achieve both, basically achieve good locality of memory access. And because for many reasons, because VM commands goes, and also because of load and dynamic load changes of the virtual machines, so if we do this, the NUMA nodes can be imbalanced, right? And we need to do rebalance the NUMA nodes once in a while. In current implementation, we try to do NUMA rebalance every 2 seconds. And if we find that a virtual machine, we need to rebalance the NUMA nodes, we pick a virtual machine, move from high-loaded NUMA node to the lower NUMA loaded one, and the virtual CPUs will be moved immediately, and also memory copying will follow slowly. Basically, in the end, we'll copy all the memory over to another NUMA node, so in the end, it will achieve local memory access again. And this is a simple case that when the virtual machine is small, but when the virtual machine is big, what do we do? So that's why we already talked about this, and I will skip the graph. It's too complicated. So, before I talk about virtual NUMA, which will deal with big VMs, let me introduce a little bit of cluster on die, since it's new to Haswell. And the cluster on die, it happens because Intel have more and more cores on certain sockets. And because the socket is so big, the cache becomes too big, and even not only memory access is asymmetric, the cache access is also not symmetric. So from one core to certain part of the cache access, it's for some, it's like, for some cache lines, it's longer than some other cache lines. So Intel introduced a cluster on die to kind of mitigate this issue, so that with cluster on die, cluster on die, you basically split the cache into like multiple pieces, and each piece is it kind of pretend it's kind of a smaller neural nodes. And with this, your local cache access latency is faster, but at the trade-off between each one sees a smaller cache. So we measured performance based on SPEC-JBB. It shows it did, with the hypercluster on die enable, it did improve performance significantly. But you need to understand the cache, right? The cache is each one's cache is smaller. So if your workload is really cache hungry with a very huge cache working set, maybe you may need to like try different options. Basically, try both have cluster on die enabled, disabled, and measure the actual performance yourself. Okay, so now we talk about virtual NUMA. Virtual NUMA doesn't matter once the VM is small, but once the virtual machine is really big, it cannot fit in a one NUMA node anymore. So what we do is we divide the virtual machine into smaller NUMA clients. We call NUMA clients, and each smaller NUMA client is scheduled the same way as I mentioned before. Basically, each NUMA client has a home node, and at any time it stays on one. It stays on one NUMA node, and memory access is on its local NUMA node, and once in a while we balance the NUMA clients. And because in a ES system we have two-level schedulers, ES does the vCPU mapping, and at the guest level you have guest schedulers that try to migrate guest threads to different vCPUs, right? And we need to expose the concept of virtual NUMA node to the guest as well, so that the guest doesn't doesn't migrate a thread from one virtual NUMA node to another virtual NUMA node frequently. So that's why we have the virtual NUMA node, and this basically both the kernel and the guest scheduler understand this kind of virtual NUMA node well. And I think here's an example. In this example, a virtual machine has 10 virtual CPUs. It is split to, and the hardware has 6 cores per socket. So the virtual machine, the virtual machine is split to 2 virtual NUMA nodes. Each virtual NUMA node has 5 vCPUs, and it can stay on. It can be placed on the socket with 6 cores pretty well. Let me see what. Okay, so here we have basically it tries to explain a tricky issue between virtual socket and the virtual NUMA node. Before ES6.5, by default, virtual socket size is 1. Virtual socket is basically you have 1 core per socket. And if virtual socket is, if you have 1 core per virtual socket, basically how we configure virtual NUMA is exactly what I described above. But if you specify non-default cores per socket, before 6.5, this number will determine the virtual NUMA node size. If you specify cores per socket to be 4, a virtual NUMA node will have 4 vCPUs per NUMA node. It's exactly the same. In 6.5, we made an improvement. Basically, we partially decouple the virtual socket size and the virtual NUMA node size. So a virtual NUMA node size now can be a multiple of virtual socket size. For example, in this case, virtual socket size is 2, but the virtual NUMA node size, we combine 2 virtual sockets into 1 virtual NUMA node to better match the hardware CPU topology. And certainly in another extreme case, if you configure the virtual socket to be too big, we will split the virtual socket to multiple smaller pieces. Each one is a virtual NUMA node. And we published a blog about the virtual machine, vCPU, and VNUMA right sizing, which have more details about this area. Please check that out. And this is basically the UI page you can use from VI client to configure cost per socket. And there's several ways, like numeric control, several command line tools you can check the virtual topology of a particular guest. I think on Windows you can use like core info. Okay, so the last topic is about VM sizing. I will skip this one is because the message is a bit confusing, I think. VM size, basically two issues, right? One is how to avoid oversizing, another is how to avoid undersizing. Oversizing, if you have, for example, for CPU first, if you have more vCPUs than what's needed by the VM, you pay two costs. So first is small CPU scheduling overhead for virtual CPU because of some, even the vCPU is idle, it has to have some timers which will kick in and it will basically cost some CPU cycles. If you're using very old system like I think Red Hat 4, basically before Linux 2.4.22 something in old days, it has even have a 1 kHz timer. In those cases, even you have an idle vCPU because of the CPU, the guest timer kicking very frequently. The amount of time wasted on idle vCPU is non-trivial. But all modern systems, including all modern Linux and even for Windows after I think Windows 8, it also introduced tickless kernel. So in those cases, the amount of time wasting on those timers are kind of trivial. But there's another aspect. Basically, if you have a lot of vCPUs, the guest will try to move thread around, and that is not good for cache or memory. Like if it's a wide VMs that are across multiple NUMA nodes, then you have like a non-local memory access issue. So if possible, try to avoid oversizing the CPU. Undersizing, the cost of undersizing is obvious. Basically, if you undersize the virtual machine, it has internal contention, right? You can see that from a lot of like guest tools. For example, you have a lot of like coolants on VM stats can be huge. Then you can see this guest is undersized. Memory is same. You have oversizing issue, undersizing issue. But memory oversizing can be more costly because for CPU, if it is oversized and it's not using it, it's idle, then CPU can immediately use it for something else, right? Memory, first, once the guests see a lot of memory, most modern guest operating systems will try to max utilizing it by using it for cache or many other things. So even though it doesn't really need so much memory, it will appear to be fully utilized. And that's one. Second, even those memory are not touched often, once it's allocated, the allocation is expensive. You need to kick it out by whatever page reclaiming technology to make it useful for other virtual machines. So the memory oversizing can be expensive. Certainly, undersizing, again, is pretty obvious. You can see internal swapping in the guest. That's something you should avoid. I think that's pretty much it's basically the end of the talk. Summary, read time is important for your performance. You need to pay attention to that. And when sizing the VM, you should, because hyper threading is not real core, you should mostly size based on physical cores instead of based on hyper threading. And we talk about some change to about how we calculate the system time. And more importantly, we partially decoupled virtual socket sizing and virtual NUMA sizing, so you should pay attention to that. And for memory, the key level message is you should avoid overcommitting active memory. And for virtual machine configuration, try to avoid undersizing a virtual machine. And so we have many other interesting talks. When you have a chance, please check that out. And we also have hands-on labs. Please fill the performance survey. Thank you. And I'm ready for questions.